Okay. So now we will discuss DC circuits. Like first, like 30 minutes or less than that even. Very quickly, we will do a rapid revision of very important concepts involved. Then straight away, we will be solving some good problems. Because in this DC circuits, you can expect some very good problems in the exam. DC circuits. So as the name suggests, these are the electrical circuits in which the power source is a direct current. And the nature of the direct current is that it does not change with time. The current and the potential difference, the current and the voltage, it remains constant. It remains constant with time. It does not vary with time. And the main component which we will be dealing with the DC circuit is the resistance. Resistance is the main component. For example, I have a very basic DC circuit which I am drawing. And this DC circuit is having two resistance, a battery. Battery has two terminals, positive and negative. The terminal with the larger length is always positive. The terminal with small length, that is the negative. So this is an example of a DC circuit where the source is the DC current. So plus, minus, plus, minus. So this is the plus terminal, this is the minus terminal, this is the plus terminal, this is the plus. And two resistance I have, R1 and R2. So this is the basic idea. Now we have two elements, active and passive, like two types of elements, active elements and passive elements. Active elements are those elements which supply energy. Active elements always supply energy, and passive elements, they consume energy. Active elements supply energy, passive elements consume energy. And here, the battery is supplying the energy, and hence battery is the active element. And the resistances, they are consuming the energy, and hence they are the passive elements. And passive elements can convert the energy. When they are consuming the energy, they can convert it into some other form. Like instead of this resistance, we can have any appliance also. We can have a bulb. If I have a bulb, it will convert the electrical energy into the light energy. If I have a electric rod, it will convert the electric energy into the heat energy. So passive element always consumes the energy and they convert it from one form to another form. So very quickly I can write passive elements consumes energy. And passive elements consumes energy and converts energy from one form to another. From one form to another form. Converts energy from one form to another form. And active elements, they supply the energy. Now see, and we have some more components like capacitors and inductors that we will study when we will be studying the DC circuits, because capacitors and inductors, they play a role, main role they play with the AC current. Initially our focus is resistance. Initially our focus is resistance. The resistors. Now the resistors, they follow the Ohm's law. And let us focus on the Ohm's law. Now let us focus on the Ohm's law. Whenever we have a DC circuit consisting only of resistors, we have to apply the Ohm's law. Ohm's law says that V is equal to IR, where V is the potential difference, I is the current, and R is the resistance. Like Ohm's law, it says that Ohm's law states that V is directly proportional to I, and hence we can write V is equal to I. So current flowing through a conductor is directly proportional to the potential difference across the conductor, and it makes sense also. As I keep on increasing the potential difference, the current flowing through the conductor will increase, isn't it? It makes sense. And let us look at some limitations of Ohm's law. That is very important. Limitations. The first is, it is not applicable to non-metallic conductors. Not applicable to non-metallic conductors. It means that the conductor, what is the conductor? Conductor is the wire through which the current will flow. So the wire through which the current will flow, it has to be metallic. Because in the non-metallic conductor, this equation will not be perfectly valid. Not applicable to non-linear circuits. Not applicable to non-linear devices. And what is the meaning of non-linear devices? Non-linear devices means that current in both the direction will be different. Meaning to say that if I have a diode, something like this device, if current flows in this direction, then it will behave separately. And if current flows in the opposite direction, it behaves differently. But resistance is a linear device. Why resistance is a linear device? Regardless of the direction of the current, the resistance will behave same. But for non-linear devices, the direction of current matters. For non-linear devices, the direction of current matters. An example of non-linear devices. We have Zener diode. We have vacuum tubes. So these are examples of non-linear devices. And one more very interesting limitation of Ohm's law. Ohm's law fails when temperature changes. Ohm's law fails when temperature changes. And temperature do uh, affect the flow of current. Fails when, and it is very interesting. Temperature do affects the flow of current through the wire. And when the temperature changes, when it increases or it falls drastically, the temperature, the Ohm's law will not be applicable. And it happens like in the severe summer, when the surrounding temperature, the outside temperature is very high, the wires they get heated, and the current flowing through them affects. And during severe winters, the current flowing through the wire gets affected. And fortunately, in the wire, the current which is flowing is alternating current and not the direct current. And hence, the influence of the temperature on the alternating current is significantly less as in, for the direct current. But still, temperature change influences the flow of electrons across the conductor. And Ohm's law fails when temperature changes. Now we will discuss one more very important law. Like this Ohm's law, though we are well aware of, like basic one. Now we will look at some advanced laws like Kirchhoff's law, which we will be using to solve the circuits. Because in the exam, you will be given circuit and you have to solve that to get some answers. So in this chapter, we will be looking at how to solve the circuits using the Kirchhoff's law. So now we are discussing Kirchhoff's law. So Kirchhoff gave two laws, the current law and the voltage law. So first we will discuss Kirchhoff's current law. Kirchhoff's current law states that total incoming current is equal to total outgoing current. The sum of current the sum of the currents flowing towards a junction, the sum of the currents flowing towards a junction is equal to the sum of the current flowing away from it, is equal to the sum of the current sum of currents flowing away from. And it makes sense. It makes sense. Because law of conservation of charge. Now let us look at one example to get a feel of it, what I'm trying to say. Let us suppose I have a junction and several wires are connected to this junction.
Sir, is node and junction the same thing?
Yeah. Node and junction is the same thing.
Okay.
Yeah. So you can call it like the Kirchhoff's node law, the same thing. So point A. Now let us suppose I have some incoming currents. Let me draw it properly. Let us suppose I have some incoming currents. I5, I4, and some outgoing currents. Now, since no net charge is created or destroyed during the process, whatever is the incoming current, that should be equal to the outgoing current. So based on that, I can say that incoming current, if I look into I1, I2 is an outgoing current, I3 is an outgoing, I4 is an incoming current, I5, I6. I1 plus I4 plus I5 plus I6 has to be equal to I2 and I3. So this is the Kirchhoff's current law. Kirchhoff's node law. I2 and I3. So this I can write. So sum of current flowing towards A is equal to sum of current flowing away from A. And one more very important discussion we have to make. If somebody asks, okay, tell me what will be the current at point A or current at node A. So current at any node or current at here at node A, current at node A will always be 0 because current is flowing through the wire, and in the node the net current is 0 because no charge will reside there. Na? So this is the Kirchhoff's current law. It's very easy, understandable also, and it is making sense also, whatever we have discussed. Now we will discuss one more very interesting Kirchhoff's law, that is the Kirchhoff's voltage law, KVL. So this we can also call it KCL. The law which we discussed, we can call it KCL, Kirchhoff's current law. Now we will discuss Kirchhoff's voltage law. This Kirchhoff's voltage law, I can call it KVL. Kirchhoff's voltage law. Now, what it is like very important. Let us understand it. So, it states that in a closed circuit, so this voltage law is applicable only for a mesh. What is a mesh? Mesh is a closed circuit. In a closed circuit, in a closed circuit, the sum of the potential drops the sum of the potential drops is equal to the sum of the potential rises. Sum of the let us see how it is done. Like what it means, let us try to understand. So in a closed circuit, the sum of the potential drops is equal to the sum of the potential rises. So let us draw one circuit to understand it. And it is basically the conservation of energy. So whatever is a drop in the energy, that will be equal to the gain in the energy in the other end. So I have a mesh or a closed circuit ABCD. Now some resistance are connected to it. R1, R2, R3. and I have a battery with voltage V. Now a current is flowing. Let us suppose the current is I. We know that in a series connection, the current remains the same. Always remember here, all the resistance, they are connected in series. And since they are connected in series, the resistance, the current will not like distributed. It's understood because let me demonstrate it. Whatever current is being generated by the battery, it will flow like this, then this, and this. No point it will be distributing to some other direction. That is not happening. And hence the current will be same all across the circuit. The current will be same all across the circuit. So the incoming current is equal to the outgoing current. Now, what is the meaning of KVL? So before that, one concept we have to understand, the concept of potential drop. What is the meaning of potential drop? Whenever the current flows through a resistance, at that segment, a potential drop takes place. Which means that here what will happen? V is the total potential difference of the battery. V is the total potential difference supplied by the battery. Now the current is, so I have three resistance, R1, R2, R3. There will be a potential drop across this R1 and I am calling it V1. Wherever there is a resistance in the circuit, a potential drop will be there over there. There will be one more potential drop here and I am calling it V2. And one more potential drop will be there across this resistance and I will be calling it V3. And what Kirchhoff's voltage law says, that is the total potential will be equally distributed among the entire circuit. It means that the total potential drop, which is V1 plus V2 plus V3, has to be equal to the total potential difference supplied by the battery. And according to the Ohm's law, what is V1? V1 is IR1. So I can say that IR1. What is V2? IR2. Because Ohm's law says that voltage is V is equal to IR and I is same and V3 is IR3. And it will be equal to V. So this is the Ohm's law. Not Ohm's law, Kirchhoff's voltage law. Ohm's law is
question.
Yeah, please tell.
So in this scenario, the I will be same, right? It won't change.
It won't change. Yeah.
It is constant, right?
Yeah, it will be same. Yeah, it is constant. Yeah. It's
Okay.
right. Yeah.
So,
Because why I is constant, why I will not change? Because there is no way to distribute I. and I will give you one example wherein I will distribute.
and what if the resistance is also same in all the three resistors?
Then R
Then
will
V
be
will
same.
be also same.
Yeah. So then the potential difference will be same. V1 is equal to V2 is equal to V3.
Okay.
Now here, one interesting observation let us make. Just for understanding, let us do somewhere here. Like what I am trying to demonstrate is how the current changes. Let us suppose I have a battery. I have a battery. Now, I have a circuit like this. Now here something interesting will happen. Let us suppose from the battery, the current I am getting is I. Now what will happen at this point, at this node? This I will be broken into two parts, two components. Like, because this current, what is current? Flow of electrons. So some electrons will flow in this direction, some electrons will flow in this direction. Current will become different. Here we say that I1 current will flow, and here we say that I2 current will flow. And once again, at this node, the flow of electrons, some electrons will flow here. I will say I3 current will flow, and here I will say I4 current. So this is how the current changes. The current breaks the flow of electrons. It has two options. Some electrons will follow one path, some electrons will follow some other path. So current will get distributed in this scenario. And we will look at these scenarios also. But here, since electrons have no other option, they only have one path to travel. All the electrons will follow this path, and hence the current will be same all across the circuit. And this is the Ohm's law. Now, like V is equal to IR, and applying the Ohm's law, we have got the Kirchhoff's voltage law, KVL. And according to the Kirchhoff's voltage law, we got this result. So this is clear to us. Now, when we are applying the Kirchhoff's voltage law, KVL, solving the mesh that we will be doing it, sign convention we have to follow. Like some sign convention. Let us look at what sign conventions we should remember or we should be aware of. Sign of EMF. That is the battery voltage source. This is one scenario. This is another scenario. A to B, A to B. In this scenario, I know that this is negative, this is positive. This is positive, this is negative. I know the convention of the terminals that I am aware of, negative, positive. Like the small terminal is a negative, the large. Now, what is happening here is that here across from A to B, I am going from minus to plus. Minus to plus means there is a rise in voltage. And whenever there is a rise in voltage, the sign will be positive. I have to take plus B. When I will be writing the equation, the voltage I have to take positive. Because in this direction, the voltage is rising, rise in voltage. Because minus to plus, rise in. So the sign will be positive. But in the second scenario, plus to minus. Plus to minus means decrease in voltage, fall in voltage. I will say fall in voltage. And fall in voltage means I have to take negative. When I will be writing the equations, I will be taking the voltage as negative. This is the sign convention for the EMF. Similarly, we have the sign convention for the voltage drop or the resistance. Let us look at that. Sign of EMF, sign of voltage drop. Okay. So let us suppose I have two circuits like resistance like this, like this, AB, AB. Let this be the plus, let this be the minus. Let this be the minus. So plus to minus means fall in voltage. In this direction, there is a fall in voltage. So whenever there is a fall in voltage, and why this terminal is having plus? Because this is connected to the positive terminal of the battery. This point A, it is connected to the positive terminal of the battery, and hence point A will be positive. And if we are going from positive to negative, fall in voltage. Fall in voltage means negative. Sign will be negative. And here, minus to plus, rise in voltage. Rise in voltage means positive. So this is clear. Now, like you have to be aware of all this, and when we will be solving circuits, you will get a clarity. Whatever we have discussed. Now we will discuss the next concept of energy sources. So we know that energy sources are basically the devices which supply energy to the circuit. Energy sources are devices supplying electrical energy. Devices supplying electrical energy to the circuit. Now these energy sources are categorized as voltage sources and current sources. So first we will discuss the voltage source, then we will discuss the current source. Voltage sources. Now let us look at the meaning of an ideal voltage source. What we mean by ideal voltage source. Okay. Now very interesting observation we are making. The main characteristic of ideal voltage source, because it is very important, the meaning of ideal voltage source. When I will say any voltage source is ideal, what is the uh, characteristics of an ideal voltage source? That is what we are discussing. So ideal voltage source, it delivers energy. It delivers energy with specified terminal voltage. With specified terminal voltage. Which is independent of the current supplied by the source. Which is independent of the current supplied by the source. What it means, we will get to it. So the idea is very simple, that ideal voltage source will forever be supplying the voltage. Its voltage will be constant. It will never drop, regardless of, no matter how much current you draw. Ideal voltage source, it will continuously give you the voltage, and its voltage will be constant. It will not change. So the graph of the ideal voltage source is something like this. Like I'm drawing the graph. First, let me draw the circuit. Like I have a circuit in which I have an ideal voltage source. This is the ideal voltage source. This is the I. This is plus, this is minus. Now, what is the characteristic of ideal voltage source is that regardless of how much current you draw, regardless of that, the voltage will always remain constant. And unfortunately, in the real world, this does not happen. The normal battery you use to power the watch, after some months, you have to change the battery because the voltage source which we use, it continuously degrades with time. But ideal voltage source is the one which will never degrade with time.
Sir, it depends on the battery, right?
Yeah,
Like
yeah.
so for the it depends on the battery, right? The
Yeah.
because for a watch you'll be using lead battery, but for
Okay.
some certain things you'll use other batteries, and I don't think you need to change them. Like the voltage,
Yeah, yeah.
I think it
No,
will.
yeah,
Yeah.
no. For other batteries also, like you will be using rechargeable battery, so you have to recharge it.
But okay, it's the same thing. Changing
Yeah,
and
yeah. Changing and recharging is the same thing, na?
okay. Yeah.
Yeah,
Got it, got it.
yeah, yeah. So the characteristic of ideal voltage source says that regardless of no matter how much current you draw, it has to be constant. It should keep on supplying the voltage. But this does not happen in the real world. The real world, the graph will be something different that we will discuss very soon. But this is the concept of the ideal voltage source. And how we can get ideal voltage source? When internal resistance is zero. So one very important characteristic of ideal voltage source is that internal resistance is zero. And unfortunately, in the real world, internal resistance can never be zero. There is always internal resistance. And hence, the batteries which we use are not ideal. So we have something called as practical voltage source, which we use. We use something called as practical voltage source. So definitely here it is not constant. So straight away I can make the graph. So first let me make the circuit. For practical voltage source, the idea is that the battery, it has a internal resistance along with it. Always. Always there will be a internal resistance in the series along with the battery. RS is the internal resistance. This is the voltage source. And the graph will not be a straight line. The graph will not be straight. The graph will be like with the current, the voltage drops. After like the voltage will keep on dropping as I keep on drawing the current. This should be the ideal behavior. But unfortunately, this is what we get. So this is the practical voltage. So there is internal resistance. I can let me bring it in the same film. Copy. Now I can discuss the current source. Like the voltage sources, we have current sources. So voltage sources supplies the voltage, current sources will supply the current. And in current sources also we have ideal current source and practical current source. So first let us discuss ideal current source. In the ideal current source, what is the property? Let us first try to understand that. What makes the current source ideal? So ideal current source delivers energy with a specified value of current with a specified current. Which is independent of the voltage. Independent of the voltage. At its terminal. So regardless of the voltage at the terminals, ideal current source will constantly supply the constant value of current. Its current will not change regardless of how much voltage we draw. And internal resistance or is zero. Internal resistance is zero. In the ideal current source, there is no internal resistance. So let us draw a circuit and the graph to understand the behavior. So I have a current source. The direction says the direction of the current. I. The current flowing is, let us suppose, and the graph so here x-axis will be the voltage. And the y-axis will be the current. So the ideal current source, current will be constant. Current will be constant always, regardless of the value of voltage you draw. Now corresponding to this, we have practical current source. That is also understandable. Very quickly, let us look into it.
So what is small I, sir? Current.
The current flowing
Oh.
because of this current source. Practical current source. So in practical current source, there is an internal resistance because of which this property is not followed. Like the current will not remain constant, but it will change with time. So I can introduce, and always for the current source, the resistance is always in the parallel. For the voltage source, the resistance in the series, internal resistance. And for the current source, the internal resistance is always in the parallel. This you have to remember. So this RS is the internal resistance. And because of this internal resistance, now this current source is not ideal. But it will drop. So this is the idea of energy sources.
So can you repeat the constant part, which is constant in what? Like in parallel, the voltage is no, the source. Can you repeat that part alone?
Okay, so this practical current source.
Yeah.
Okay, so yeah, in practical, like always remember, in the practical current source, the resistance, the internal resistance of the current source has to be in parallel with the current source. Whenever we are having a current source, the internal resistance will be in parallel, and whenever we are having the voltage source,
Hmm.
the resistance has to be in the series. Internal resistance has to be in the series.
Okay, so got it.
Okay. Now let us look at some problems.
Sir,
Now,
why is the
yeah.
sir, why is any specific reasons?
For this,
Yes, sir. For current, the resistance is in parallel, and for voltage, it is in series.
there is a reason. I will tell you the reason.
So can you write that down? It's just confused. I mean, I understood, but like when I'm writing it, I just
You just remember this.
Okay.
I will tell you the reason. Like you just remember this circuit. You will never forget. Just make a mind map of it. Like current source, internal resistance has to be like this. And for voltage source, like here voltage source, this I will highlight it. Internal resistance has to be like this. Just this circuit, if you remember, don't need to write
okay.
also.
So basically, current source,
Yeah.
it's in series, and like for voltage, it will be in parallel.
No.
Current it's parallel, voltage is series.
Yeah.
Okay.
That
Oh yeah, the figure is better. Yeah, okay, got it. No, it just
Yeah.
I just didn't look at the figure properly. No, yeah.
yeah, nice. Yeah, just a figure if you remember, you will never forget it. And it's very important. Because when we will be doing numerical, so many times you will revise it. So you will get an idea. Now I will tell the reason. So reason is that see, internal resistance has to cause a obstacle. And see, tell me one thing. With the current source, if I introduce a series resistance, nothing will happen. Why? Because the flow of current will be same. The current will not at all distribute. The current value will not at all change. But if I have a resistance in parallel, then what will happen? At this point, there is a leakage of current with time because this some of the electrons they will flow in this direction, and the current I will be drawing at this point, it will not be equal to the capital I, but it will be something less. Why something less? Because this resistance in the parallel, it will suck some electrons, because of which leakage of electrons will be there, leakage of current will be there, and the current which I will be drawing, that will be not equal to capital. And hence this internal resistance is responsible, it is degrading the quality of the current source. More the internal resistance, the quality will degrade more and more. And the same reason is applicable for this voltage, because this resistance in series is responsible for the voltage drop. It is dissipating some energy. This resistance in the series, it is dissipating the energy, and hence the Kirchhoff's voltage law, it is not 100% applicable. Like Kirchhoff's voltage law says that whatever is the energy of the battery, it should be equally distributed, but it does not happen because there is a leakage of energy because of the internal resistance of the battery, which is connected in the series. Okay, now let us focus on problems. Let us practice some questions. Because here we have to feel the problem. If you feel the problem, then regardless of whatever they will ask, we will do it properly. It's about understanding the concepts. Now let us do some practice problems. I will be writing questions fast, like small questions they are. And our goal is to understand the question, then attempt it. Because in the exam, you might expect any question, and you should be able to solve it.
So you just write the questions, I'll be back.
Okay. What will be the current drawn? What current drawn by a lamp rated at 250 volt, 40 watts. So this is the power rating of the lamp. Now what it is, you will get a feel of it. So I have a lamp with this rating, and it is connected to a connected to a 230 volt supply. It is connected to a 230 volt supply. So let us see how to solve this. In this question, I have a lamp and the power rating of the lamp is given. It means that the lamp I have, it can operate at max at a voltage of 250 volts. Above that, it will blow. So at max, you can pass a voltage of 250 volts to power that lamp. And the power consumed by that lamp is 40 watts. So the approach is that, okay, whatever quantities are given, let us start with that only. Like, let us start writing that. Then we will be able to correlate with some of the formulas which we know. We can apply it and we can get to a solution. So the first, what I can do is that I can make a circuit wherein I have a lamp. Lamp, I can call it a bulb. I have a battery, and since what you say that AC is not defined. So whenever AC is not specified, we have to consider it is DC. This DC. 230 volt. And I have the bulb. I have the bulb. Now this bulb is 40 watts. And what I have to find in this question, I have to find the current. Definitely, when this bulb is connected with this battery, some current will flow. And what will be the current that will be flowing? That I have to find. Let us see how to do this. So here in this question, the rated power is given, power rating of the bulb. And the rated power is 40 watts. I can just write W also. It's understood. Then rated voltage is given. This rated voltage 250 volt. Okay. Now see, ultimately, if I can calculate the resistance offered by this bulb, then the Ohm's law I can apply. Why I can apply the Ohm's law? Because it's a DC circuit. In the DC circuit, if you don't know the resistance, you know the voltage, current, you can calculate. It's a DC circuit. So resistance offered by this bulb, I can calculate using the formula P is equal to VI. And simplifying it. How to simplify that? Let us see. See, I know P is equal to VI. Here, P and V I know. Because VI will be taking the rated voltage, not the supplied voltage. Because I have to calculate the resistance offered by the bulb. So I can write Ohm's law. V is equal to IR. Since V is equal to IR, I will be V by R. So instead of I can write V by R. So I will get one more formula, P is equals to V square by R. Or R is equal to V square by R. And if I put it, what is V? 250 square. And what is P? 40. I will calculate the resistance offered by the bulb. And if you solve this, you will get something like this. 1562.5. Ohm. This is the resistance offered by the bulb. So resistance I got. Now I can simply apply the Ohm's law. Now I can apply the Ohm's law.
Sir, what is P equals to VI?
Oh, so in class 12, you might have studied P is the power, V is the voltage, I is the current.
Yeah.
So power is voltage into current. It's a formula. If you don't know, you
okay.
remember it. Yeah.
Okay.
Power is voltage into current. And we know Ohm's law, V is equal to IR. So I can write V by R. So
Yeah,
P
I
will
understood
become,
that.
yeah. Now applying Ohm's law. Yeah. Now ultimately current drawn, which is I, it will be V by R. And here what will be the V? V will be the 230. And what is the R? R is the resistance of the circuit. Exactly. 0.1472. This is the answer. Now let us look at the second problem. Let me write the second problem. A resistor I have a resistor with a current of 3 ampere. I have a resistor with a current of 3 ampere. So converts also like 500 joule, 500 joule of electrical energy into heat energy. In 12 seconds. And we have to calculate what is the voltage across the resistor. What is the voltage across the resistor? This is what we have to find. So here, basically, we have a resistor and the current flowing through that is given 3 ampere of current is flowing through it. And the resistor, it dissipates 500 joule of electrical energy into heat energy. So the energy dissipated by the resistor is given the current flowing through the register is given and the time is given. Like it takes 12 seconds for the register to dissipate that. And we have to find the voltage across the register. So here we can make use of one formula. See, what is work done? Work done is power into time. Power is work done upon time. So work done is power into time. And what is the work done? Work done is like energy which is dissipated. See. And I can further write it. It implies that work done is equal to what is power? V into I. So V into I into T. Here W I know 500 Joule. I know 3 ampere and T I know 12 seconds. So I will write the V which I have to calculate. V will be W upon IT. $500 upon 3 into 12. 13.88 volts. This is the answer. The idea is that you should be aware of some basic formulas that I am making you aware with these problems, because these are like the concepts which you have already discussed, studied in class 12. So P is equal to VI and work done is power into time. So VIT. And here Ohm's law also you can apply. So instead of V, you write IR. So it will become I square RT. Depending on the parameters which are given, you can play with this. You can modify it according to your need. And in the exam, you have to write it properly. Here, though, since we are in a hurry, I don't want to write each and every step. You write given the energy dissipated, that is the work done, is equal to 500 joule. The current flowing through the register is equal to 3 ampere. I is equal to 3 ampere. Then the time taken for the energy dissipation, small t is equal to 12 seconds. You have to write all that given. Then write the formula according to the formula. Work done is equal to power into time. So it should be a good solution which you have to present. Then you will get full marks. If you just do this, they might cut marks, because it is a subjective paper. Now you will be given. So that is you have to take care of that. That all I will not do now, because we have to rush. We have to study so much. I am just making you aware of how to solve the problems. Next problem. So we have 20 lamps. We have 20 lamps. Each of 60 watt. Are used each for 4 hours a day. 4 hours of day per day in a building. So in a building, we have 20 lamps which are being used 4 hours per day. And every lamp consumes 60 watt power. Now I have to do like calculate. I have to calculate current drawn when all the lamps are working. Current drawn when all the lamps are working. Second, the monthly electricity charge the monthly electricity charge. It is given that per unit the charge of 1 unit is 55 paisa. $55 paisa. And the voltage supply is 240 volts. So in this problem, what are the data points which are given to us? The power consumed by a lamp is given and the voltage supply is given. And these lamps are like 20 lamps, they are connected. Now see, one very interesting thing I will discuss. Like whatever is given, first let us visualize it. Whatever is given to us, let us visualize it. So 20 lamps are connected. So every lamp is acting like a resistance because it will be consuming energy or it will be dissipating energy. So like this 20 lamps will be there. And they are connected to a power supply of 240 volt. And since AC is not specified, so by default, if AC is not specified, then we have to consider it to be the DC. Because if it was AC, then the method was different. That we will discuss later on. We will discuss AC circuits also. So this is 240. Now it is very clear that we have already seen the Kirchhoff's voltage law. This 240 volt, because every resistance, there will be a drop. There will be a drop in the voltage. And since the bulbs are similar, the resistance offered by them will be same. Because bulbs are similar, so all the bulbs will offer the same resistance. It means that this 240 volt will be equally distributed. Like voltage drop will be same across each bulb. Okay. So this will be a scenario if the bulbs are connected in series. And there is one more scenario. Like I am giving you both the possibilities. And one more scenario is bulbs are connected in parallel. Bulbs can be connected in parallel also. That is what we are discussing. The two scenarios I am discussing. If the bulbs are connected in parallel, let me draw it properly. So 20 bulbs they are connected in parallel. And they are connected with a battery. Now you tell me which one is more efficient, which you will prefer.
Parallel.
Parallel. Very good, very good. That's the right answer. Very nice. We will prefer the parallel, and there is a reason for that. And why you will prefer the parallel?
Because in series, if one bulb fails, everything will fail. Like
Very
you can,
nice.
yeah.
That's the right, precise, perfect answer. The drawback with the series is that if one bulb fails, entire all the complete system will go down, and hence in the the electric connections we use, everything is parallel, so that if one segment goes down, other segments they keep on working, so that all the segments or all the appliances that they be independent of each other, and that is possible with the parallel connection. Now in the parallel connection, the voltage will be same for all the resistances, current will be different. So the voltage received will be same, the current will be different. So we will not choose this one, rather we will be choosing this. And why I like presented both the scenarios, because in this question nothing was specified. Nothing was specified that how the bulbs are connected. The students, they make mistake. Sometimes they think that bulbs might be connected in series and solve it, and they get the wrong answer. So always when nothing is given, we have to select the ideal scenario. So this is the ideal scenario. Now we can very easily calculate the current drawn by all the, like every bulb. Current drawn by a single bulb. Let me write it. Current drawn by one lamp. We know P is equal to VI. So I will be P by V. I know the power.
1/1. Yeah.
Yeah. I know the power of the bulb, 60 watt. And voltage will be same for all the bulbs. So 240. So the current drawn by every bulb will be 0.25 amp. Every bulb, like 20 bulbs I have, every bulb will draw a current of 0.25. Now the total current drawn, because in the first part they are asking current drawn when all the bulbs are working. So every bulb is drawing 0.25 ampere. So very easily I can calculate the total current drawn. Total current
5.2. 5.
Yeah. Total current drawn by 20 volts. So we will multiply this with 20. Like 20 into 0.2. 20 into 0.25. It will be 5 ampere. This is the first answer. 5 ampere. Let me write it to emphasize the answer. Okay. Now we can do the second part also. Monthly electricity bill that we can do. So energy consumed per month we can calculate. Second part, we have to calculate the energy consumed per month. And based on that, we will get the electricity bill. Energy in a month. Now see, idea is this, that 4 hours daily, let us suppose 30 days. So total 120 hours. Okay. So total the bulb will work for 120 hours. One bulb will work for 120 hours. And in total, we have 20 bulb. And every bulb is consuming 60 watt. So this will be the watt hour. Why watt hour? Because I have kept hour only. Watt. Once
You
again,
convert it into seconds, sir. Like, okay, hours per day.
yeah,
Okay.
yeah. Why we are not converting it in second? Because the unit, it is given 55 paisa. It is the kilowatt hour.
Per
Like
hour. Achha.
yeah,
Okay.
one unit is the 1 kilowatt hour. Like this, whatever what I will get, I will convert it into kilowatt hour, and based on that, I will get the units, and I will multiply that unit with 55 paisa. Like here, one thing which I should know is that 1 unit is equal to 1 kilowatt hour. I will write it. One basic. I am telling you, 1 unit is equal to 1 kilowatt hour. Based on that, I can solve. Convert it to kilowatt hour, I will get the number of units, I will multiply it with by paisa. Once again, I will tell what I did. 4 hours daily, I have to calculate the monthly bill. So 4 into 30 will be the total number of hours by the one bulb. I have 20 bulb, so into 20, and every bulb is consuming 60 watt. It is given in the question, into 60. This will be the energy consumed in a month by 20 bulbs. And when you solve this, you will get, and to be more precise, here itself I can divide it by 1000 to convert it into kilowatt. I will divide it by 1000 to convert it into kilowatt hour. And now whatever I will get, that will be the units consumed. So it is when you will solve this, you will get 144 kilowatt hour. And since 1 kilowatt hour is 1 unit, I can say that I will get 144 units. And 55 paisa, it will be 0.55 rupees. I can divide it by 100. So the bill I can calculate. Monthly electric charge I can calculate. And the monthly electric charge will be 144 units into 0.55 rupees. It's a per unit charge. I will get the bill of rupees 79. This is the answer. Let us solve some more problems. Now we will be doing some circuit solving. Circuit problems we will be doing. So I will be drawing a circuit, and in that circuit, we have to find the value of current. Find the value of current. 200 ohm. Let me draw the circuit to get an idea. So we have a circuit something like this, wherein I have a battery, $100-volt battery. It is connected to some resistance, some more resistance. Here also we have resistance. Here also we have some more resistance. Now I can name the values. 100-volt battery, 120 ohm resistance, 150 ohm resistance, 40 ohm resistance, and 100 ohm resistance. This is the plus, this is the minus. And we have to find the current flowing through the 100 ohm resistance. So let us give it a try. Now definitely, if I break it into current, like from the battery, I am getting one I1 current. Now that I1 at this junction, at this node, it will distribute into I2 and I3. And for both 40 and 100, the current will be I3 same. This is I2, this is I3. And we have to find the I3. Once we are able to find the I3, then we will be able to find the current flowing through the 100 ohm. Because 40 ohm and 100 ohm are in series, so the current flowing through the 100 ohm will be the I3.
Sir, I have a question.
Yeah, tell.
Can I write I2 instead of I3? Matlab, I can replace their positions, or is it?
Yeah, you can. You can
Oh,
take it whatever you want. Ultimately,
okay.
whatever current you are taking it here, that will be
Yeah,
the
that
current
will be 100 ohm.
that will be flowing through 40 ohm, and that will be flowing through 100 ohm.
Yeah, okay.
And that is what your answer will be. Now I got an idea that in order to solve this, like what they're asking, I have to just calculate I3. That's it. I'm done. Calculate I3 and you will get the answer. Now, whenever there is a scope of simplifying the circuit, we should do that. So we know that whenever two resistors are in series, we can add them. So we can do a certain level of simplification.
So, but then we can't add 40 and 100, right? So even though they are in series,
Yeah,
I cannot do that, right?
why?
No, because if I add them together, then I won't be able to find them individually, or can I find
Yeah.
them?
No, so ultimately, now, regardless of this resistance, I3 will be the one I am interested in. Now, I am not at all interested in 100 ohm. I am interested in I3. So if I merge them, then also the current will be same. It will be I3 ohm. The current will not change. The current which I have to compute, that will be I3. And hence I can combine them. Like now I am redefining the problem. What they asked is find the current to 100 ohm. And with analysis, I found that I have to find I3. I3 is the current through the 100 ohm. If I merge these two, I3 will be same. I3 will not get changed. I am redefining the problem. I am simplifying the circuit. Make it parallel. One 150 ohm, 100 ohm. Okay, not 100, 140. Because I'm adding both. 100 plus 40, 140. 100 volt. This will be the plus, this will be the minus.
So, but then we'll be finding the current through 100 ohms, 140 ohms, right?
Yeah, that will be I3 only. Now we have changed the problem. Now our problem is to calculate I3.
Okay, not the current through 100 ohms. It doesn't matter if it's 100 or 140.
Yeah,
Okay.
because we have seen that I3 is the current which is flowing through the 100 ohm. So I3 I
It
have to
doesn't matter.
just,
Okay, okay, got it.
it doesn't matter very much. That's all. Now see, like in order to do this, there are different ways. Like you can apply the mesh rule. That also you can do. But I am applying a different technique wherein first I will be calculating I1, and once I know the I1, I will be using the current division rule that I will discuss here itself. And because this I1, it is getting divided into I3 and I2. So if I know the I1, then easily I3 and I2 I can calculate. And if I know the I3, then though it's done. The problem is solved. So how to calculate I1? I1 is the current drawn from the battery. So if I am able to calculate the net resistance and apply the Ohm's law, I1 I can calculate. That is what I am trying to do. That is what I am trying to do. So how I will be doing that? Let us see. So see, we know that these two resistance are in parallel, 150 and 140. They are in parallel and they are further in series with 120. So I can write R net here itself. I will write R net is 120 is plus these two resistance are in parallel, and I know that whenever two resistance are in parallel, that net resistance will be the multiplication of both divided by the addition of. Because here we are making use of that formula 1 upon R is equal to 1 upon R1 plus 1 upon R. Whenever two resistance are in parallel, we use this formula. And here R will be equal to R1 into R2 upon R1 plus R. Okay. Now we can solve this to get the net resistance. And we will get 192.41 ohm. This is the net resistance. And if I get the net resistance, then I1 I can calculate. Ohm's law. I1 will be V is equal to IR. I is equal to V by R. V by R net. V is 100 volt. R net is 192.41. It will be 0.519. Now I got the I1. Now since I got the I1, now I can calculate I2 and I3. How I will be doing that? Let us discuss that. Current division. So now one formula I am writing very important to this. I3 will be the total current flowing, that is I1, the total incoming current I1 into the resistance on the other side, that is 150 on the total resistance, like 150 plus 140. So this technique you should remember. Once again, I am telling you. I3 I have to calculate. Like I know the total incoming current. If I know the total incoming current, what will be I3? I3 will be total incoming current, that is I1 into resistance in the other terminal, because the total current is getting distributed into I3 and I2. So the resistance of the terminal through which I2 is flowing upon total resistance, that will be 150 plus 140. This you have to just remember it, and then I3 we will get. So this is known as current division rule. I1 is 0.519 into 150 upon 290. And when you solve it, you will get the final answer. That is something like 0.268 ampere. And this is the current flowing through the 100 ohm resistance. One more question we will do.
So can you explain the RNet again? What did you do there?
Okay. So see, you are like comfortable with this now? 140.
Yeah, that one I have understood.
Now see, in this circuit, these two are in parallel.
Okay.
And whenever two resistors are in parallel, we apply this formula. 1 upon R is equal to 1 upon R1 plus 1 upon R2. Like 1 upon R is the net resistance, no? Net
Okay.
resistance when two resistors are in parallel. So net resistance will be 1
Net
upon R1.
resistance of only those resistors which are in parallel, right?
Yeah. That is right. That is
120 ampere is not included here, right?
that is not included.
Okay.
So
Now-
it will be So when we will simplify it, it will become R1 into R2 upon R1 plus R2. So
Okay.
a simple trick is that whenever two resistors are in parallel, just apply this formula to find the net resistance. Multiply two resistance, divided by add them. So first we multiplied, then divided by add. Now whatever the net resistance we will get, it is in series with 120.
Oh, then we just add that.
We just add, and we will get this. So this is the net resistance. So all this we can convert it into a single resistance. That is the net resistance.
Yeah.
And we make use of that. Ohm's law. So the total current drawn will be the total resistance, net resistance, and voltage. V is equal to IR. I will be V by R. So V is 100 by R. 0.519 ampere. Now this is the current division rule. Current division rule says that total incoming, like I3 you want to find. I3 will be total incoming current into the resistance across the other terminal 150 upon total resistance 150 plus 140. Because I1 is getting divided into these two terminals, I2 and I3. So this formula, this technique you have to remember, very important. Like in some more problems you will come across this. You will get an idea.
Sir, why did you take the resistance of the first resistor? Why not 140 instead of 150 for I3?
Okay, so why we have taken 150 and not 140 here?
Yeah.
That's the formula. We have to take it like this. So you have to remember this, that I3, if you have to calculate I1 total incoming current into the other resistance, because see, for I3 what is the resistance? 140. So we are not interested in that. We are interested in the other resistance. Other resistance is 150. So I1 into 150 upon total resistance. So this is the formula, you have to remember it. There is a derivation for that. All that is not interested, like we are not interested in all that. Because ultimately in the question you have to solve the numerical.
What
the
if
exam.
what if there was another resistor connected in parallel? Then which one would we have taken?
Yeah, that's a nice question. So then we will be applying a different technique, and all that we will be seeing because we will be doing lots of numericals.
Okay.
Every scenario will be covered one by one.
Okay.
Okay, now let us look at the next one. We have a circuit in which we have some batteries. We have a resistance. So this is the R. This is the 20 volt battery. This is 8 volt. This is 10 volt. This is 5 volt. And this is 7. So here batteries are connected with each other and there is a resistance R. And let me highlight the terminals. Positive, negative. Positive, negative. Negative, positive. Positive, negative. Negative, positive. Okay. Now here in this question we have to find the value of R. Now what I can do is I can apply the Kirchhoff voltage law with the sign convention.
So
Sign-
what is asked in the question?
In the question it is asked find R.
Oh,
Fine. Now in order to solve this, I will be writing an equation wherein I will be using the Kirchhoff or the sign convention for the battery, wherein we have seen that two scenarios we have seen. Let me write. Two scenarios we have seen. Voltage drop and voltage rise. Whenever there is a voltage drop, there is a negative we have to take sign. Sign we have to take negative. And wherever there is a voltage rise, we have to take the positive. We have to take the sign positive. Now let us see. First we will be like, let us suppose we are starting from 20 volt, then 20, then 8, then 10, and then 17, then 5. And let us suppose the voltage drop across R, let it be V1. Because we have seen that every resistance there is a voltage drop. Let it be V1. So what will be the equation? Let us write it. Now 20. What will be the sign of the 20? Since voltage is rising, minus to plus, so it will be plus positive. For 8, the voltage is dropping, so minus 8. For 10, voltage is rising, so plus 10. And for this V1, uh, V1, how we will uh, consider the sign? Okay, so what we will do, we will take it other side. We will take it other side. For now, you ignore the V1. For now, you ignore the V1. And this is V, because here both are plus plus now. So we cannot decide. So we will take it other side. Now let us focus on 17. In the 17, there is a voltage drop. So minus 7. And for the 5, there is a voltage rise. So plus 5. So this sum of voltages will be equal to this V1. And the question, sorry for this question, they are asking find.
It would be okay. Sorry. Yeah.
Yeah. Okay. One correction I will do, then we will discuss. Question is find voltage across R, not R. Find voltage across. And voltage across R, we are considering it to be V1. So we have to find V1. Yeah, tell.
Sir, I'm getting V1 as 1. So R1 would be also
Okay, let us cross check it. So it will be 30. Uh, so minus 3, minus 20. So V1 should be 10 volt. 10 volt is the answer. Answer is 10. Voltage across R 10. One more question. And here this loop we have applied, it is the KVL. I can mention that. I can mention applying KVL. One more question we will do. So we have a circuit. Current source. connected like this. Ten ampere, 5 ampere, 12 ohm resistance, 2 ampere, 4 ampere. What is asked in the question is find the current through the 12 ohm resistor. Find current through 12 ohm resistor. This is what is asked. Now, how to do this? Now, see, the idea is that Kirchhoff's current law says that total incoming current is equal to total outgoing current. So, what we can do, the current in one direction, the current in the same direction, we will add the one side, and current in the other direction, we can add in the other side and equate them. So, by KCL, like current in the one direction, I am adding it together. So 10 ampere, just I will write 10 and plus 2 plus 4. It is equal to 5 plus I1. And when I simplify this, I1 I will get, okay, let me do it properly. So 16 will be 5 plus I1. It implies that I1 is equal to 11 amp. So I can say that because I1 is the one I have to find now, according to the question. I1 is the current flowing through the 12 ohm resistance. So current flowing through 12 ohm resistor is 11 amp. This is the answer. So today we will keep it in here.